Well, hello everyone. Today we get to learn our last topic in our polar unit, but we'll of course learn it remotely. Now, I really want to encourage you to treat this as if you were in the classroom. In fact, we're going to be using Desmos, so having Desmos handy, maybe opening it up on another tab on your computer or your phone, and even a calculator like you almost every day we would use in the classroom. I really encourage you to have that handy. Um, so yes, take some notes, but also participate, um, because the other thing that you would be doing in the classroom and that we're still going to do today is at the end of the lesson you would be given three problems to solve. And these three problems, of course, will be like today's lesson. But instead of just making them homework, I'm going to make it like a mini assignment. That's what I would have done in the classroom. Also, what that means is, yes, I want you to complete the three problems, but I want you to try to complete them with a little bit more care, a little bit more of a desire to try to get them right, because you're going to hand them in. You're going to hand them in, and most of the grade, not all of it, but most of the grade will be based on correctness, just like any assignment. So pay attention, participate, and then be ready to work out three problems related to today's lesson. So what are we talking about today? Well, polar systems is what we're talking about. We're gonna work on polar systems. Now remember, polar is r and theta, and systems, well, that should be something that you would have talked about back in your algebra classes for a few years. Let me just remind you, or let me show you a system, so that you can kind of be reminded of what we're talking about. Remember, systems are made up of two or more equations. We're just going to stick with two. And when you solve a system, what you're really doing is you're solving for a point that actually satisfies both equations. So here we have a polar system. R equals 5 sine of theta, and R equals 5 minus 5 sine of theta. Now, before we solve those, let me give you a couple other system reminders. These are just reminders, so maybe you just want to listen, or you can write them down if you want to. But don't forget that the solution to a system, as I mentioned, is going to always be the intersection of the lines. So when we're solving a system, you might say that we're looking for an intersection. Sound familiar from your algebra classes? How about what's next? This looks like a little scratch off here, so I'm going to scratch this off. It looks like solutions are written as points. Right, solutions to systems are always written as points. What that means is that you're really going to end up with two numbers, r and theta. So we're solving for both r and theta. And it looks like we have one other scratch off here, so let's see what this says. It says solutions must work in all the equations. That's correct. Whenever you find a solution, in other words, a point, it's going to actually work in both of the equations. And that'll actually be very important as we get into the lesson, when we discover that sometimes a point doesn't work in both the equations, which means that that it's not actually a solution. All right, so here's some solution reminders. Are you ready to get down and busy solving this first system? Now, there's two methods that we'll use to solve a system, and one of those methods is called the graphing method. Now, to do the graphing method, we're going to use Desmos. So again, if you don't have that ready, in fact, what I encourage you to do is to type in these equations. We'll type in the first one, r equals 5 sine of theta. Now, as you type that in, or maybe before you type it in, what type of graph is that going to be? Remember that chart that we made long before Christmas break? That's right. That 5 sine of theta that's going to graph as a circle. When you have your test in a couple days, you actually have to know, because you're going to study that chart a little bit, that 5 sine of theta is a circle. So what's our other graph? 5 minus 5 sine of theta. Now remember, when those two numbers are the same, 5 and 5 are the same, we end up with a special shape. Did you type it in? Do you remember? It's a cardioid. And again, in a couple days when you have that test, you guys will hopefully study and you'll know that that was going to be a cardioid. Okay, well, we're not taking the test right now. We're just solving a system. And remember, the solution to a system is the intersection of the lines. So honestly, right now, it's a visual thing. As long as you changed your settings, I forgot to remind you, but did you change your settings so that it was in degrees? And did you hit the little grid that is the polar grid? So now it looks like I can kind of just visually look at this and see where we have the intersection of these lines. Now it appears that right here in the middle, we have an intersection point. And in fact, there is. And that intersection point, because I have rotated and also because I have moved 0, so remember it's r equals 0, but I've rotated 0, I get the point 0, 0. Now be careful, 0, 0 doesn't mean that x and y equals 0. It means r and theta equals 0. Well, as I continue to move around the circle, which is actually what's happening here, I seem to get another intersection point. Now you got to understand that this is just a visual thing. So visually, I feel like that intersection point is on 30 degrees. I feel pretty good about that. So 30 degrees is my theta. And then if I count out my circles, I count out 1 circle, 2 circles, and not 3 circles, but 2.5. Now, before you say, whoa, how am I supposed to know that that's 2.5? I'm never going to give you a point that's anything other than a whole number or a half number. So yeah, that means that I have the point 2.5, 30. Remember now, this is just visual. So I'm looking at my Desmos and I'm basically finding these points of intersection. Did you find that one already? Remember, the R value, it looks like, would be 2.5. The theta value is on the 150. Now, are those my only 3 points? Well, as I continue to go around my circle, I actually get back to the beginning. But it's funny, when I get back to the beginning, it's actually a different point. It's the point 0, 180. Well, that's because I've rotated 180 degrees around that circle. So yeah, 0, 180 ends up being a different point. Well, this is interesting. I have what appears to be 4 points of intersection. Now, what we're going to do is we're going to find out, are they really points of intersection? In other words, do they work? Do they work in all the equations? So what we're going to do is we're going to carefully do they work in all the equations? So what we're going to do is we're going to carefully take these points and we're going to plug them back into the system. Now, to plug them back into the system means that I'm going to use my calculator. And I decided that I'm going to start with the last point that I found. Now, just so you don't get confused, I'm just using the last point just for something a little different. And what I want to do is I want to show you how we're going to plug in the point 0, 180. Now, when I plug that into the two equations, really what I'm doing is I'm plugging 180 in for theta. Now, when I plug 180 in for theta, it would be like I'm doing 5 sine of 180. It would also be like doing 5 minus 5, the sine of 180. Now, I encourage you to pop those in your calculator and notice that you end up with some R values. Now, it looks like the first R value makes sense. I get 0, which, if I remember correctly, that was the R value I was trying to get from my point. But the second one, when I plug it in, I actually end up with an R value of 5. Now, how can this be? Well, it turns out that because the second R value is 5, it's not the R value that I was hoping to get. Remember, I was hoping to get an R value of 0, but it comes out to be an R value of 5. And what that means is that when you plug in 180, it doesn't work in all the equations. In fact, ultimately what that means, I'm going to cross off this point because it's not actually a solution to the system. Let's try another point. Now you'll notice here I'm just kind of working backwards. So let's try the point 2.5, 150. Now remember, when I say try it, that means that you're going to plug 150 in for theta. So we're going to do 5 sine of 150, and we're going to do 5 minus 5, the sine of 150. Now, what kind of R value am I hoping to get? That's right, I was hoping to get an R value of 2.5. That, of course, is what it said when I originally wrote the point. And is that what happens? Well, in fact, it is. That means that 150 does work in both the equations, which means that the point 2.5150 is a solution. Now, since it's a solution, I'm actually going to circle it for real, or I'm not going to cross it off. Now, what I want to do is encourage you guys to test these last 2 points. That means you should be plugging in 30 for both of the thetas, see what happens, and then you should be plugging in 0. Go ahead, you can pause the video, pop them in your calculator. And what did you find out? You should have found out when you plugged in 30 that it did work in both the equations. That's because you came up with an R value of 2.5. But when you plugged in 0, you should have found out that it didn't work in both equations. You did not get an R value of 0 for both of them. So we'll cross that one off. So what do we have? Well, we end up with 2 points that ultimately are the solutions, and we found them using a graphing method. There's another method. It's called the algebraic method. Now, before you say, do I have to? Yeah. I want you to understand both methods. Also, some kids will say that the algebraic method is easier. And honestly, when you do your exit assignment, I'm going to ask you to solve at least one problem with graphing and also one problem with algebra. So let's try it. Now, the nice thing about the algebraic method is it kind of takes us back to systems of equations in your algebra classes. And there was something that you did in that class. It was called the substitution method. You see, if r equals 5 sine of theta, then I can certainly plug that in to the other equation, and I can plug that in for r. Now, when you do that, you end up with a simple statement that 5 sine of theta equals 5 minus 5 sine of theta. And actually, what I've done now is I've created an equation that I can solve, kind of like we solved in the last chapter. How do you solve an equation like this? Well, you just want to gather your variables on one side. In this case, it would be pretty easy just to add 5 sine of theta. Yep, that's going to give you 10 sines of theta. Now, 10 sine of theta equals 5, so that means I can divide by 10 and very quickly say that the sine of theta equals a half. Now, the sine of theta equals a half. If you're quick on your calculator, you could do the inverse sine of 1/2. And I'm going to be honest with you, there's nothing wrong with that, but there's a little bit more to this problem than just doing the inverse of a half. And if you'd allow me, I'm going to take you down a little road that leads us to some theory. Now, remember the unit circle? Yeah, the unit circle says that if the sine of theta equals 1/2, that means that since sine is y over r, that means that the y value is 1 and the r value is 2 on a triangle. Now, a triangle that has a y value of 1 would be a positive y value. So that means that my triangle is definitely going to be going upward as a positive y value. Now, I know we're going back to some theory that we haven't talked about necessarily yesterday, but basically the triangle that I just drew has a sine equaling 1/2, which basically means the y value is +1 and the r value is 2. Now, as you make a triangle like this, you might just maybe notice that it's a special triangle. That's right, it's a 1, 2, root 3. Now, when you notice it's a 1, 2, root 3, then you have the ability to say that the angle that's across from 1 is 30. Because remember, a 1, 2, root 3 is a 30, 60, 90. We're doing pretty good, but there's actually another triangle that has a sine value equaling +1/2. That basically means that there's another triangle that has a positive y value. That's right, it's the triangle that's over here. Let me make that just a little bit bigger. There we go. And the thing about this triangle is that it also has a positive y value and an r value of 2, which, yep, it makes it a 1, 2, root 3. Now, technically, that's a negative root 3, but it's actually not that important for this problem. What's important is that we realize that 30 degrees is going to squeeze in there across from the number 1 again. Now, remember, we're trying to solve this equation that says the sine of theta equals 1/2. Sometimes kids are like, how do you solve that? Well, what you're really doing is you're looking for theta. And theta is actually going to be the rotation to get to each of these terminal sides. Now, that's kind of fancy talk, which basically means what's the rotation to get here? Well, yep, it's 30 degrees, as we already discovered that that's the size of that angle down there. It's actually called a reference angle. But what about this terminal side over here? Yes, that terminal side actually contains another theta. Now be careful before you say that it's 30. No, it's not 30, but it does have to do with 30. You see, it's going to be the rotation to get over here. Notice that I rotated from 0. So, I'm 30 degrees shy of 180, which is why we can argue that it's 150. Now, do you recognize those two numbers? That's right, they're the same two angles that we found in the graphing method. But now, using an algebra method, we're able to say that there's a point that has a theta value of 30 and 150. Of course, that would be another point. All we need to do is get the r value. Now, geez, where do you get r values from? That's right, you get them from the equation. And what you can do here is you can plug 150 back into both equations. Wait a minute, we already did that. And when you plug 150 in, you end up with 2.5. So I can now really legally say that r value is 2.5. And did you already plug 30 into your calculator? You did. And it also comes out to 2.5. So we end up finding, of course, the same two answers, but we found them with an algebraic method, and we even threw in a little bit of theory. Okay, now, those are your two methods for solving a system. Honestly, every system kind of behaves the same way. So instead of going over another problem, what I'm going to ask you to do now is use the exit ticket that I attached in the post and very carefully solve each of those problems, one of them with a graphing method, one of them with an algebra method, and then you choose how you want to solve the last one. You can use either method. As a little bit of a hint, you can't use the algebra method on the last one. The equation that you create is actually impossible to solve with algebra. So you're going to want to use the algebra method for 1 and or 2. All right. Now, I'm still here to help you. You can certainly call upon me. Otherwise, you're going to want to have those 3 problems solved like a little mini assignment that you're ready to turn in tomorrow. That's graded mainly for correctness, but also, of course, to give it a good shot. Okay? Hey, have a great day.